Hello, everybody. We're Group 9, and our group members are Azad, Nina, and Ben. Our presentation is on predicting the cardiovascular disease using the applications of machine learning. So what is cardiovascular disease? Cardiovascular disease are a group of disorder of the heart and blood vessel. They are the #1 cause of death globally. We are also going to be looking at body mass index and how it relates to cardiovascular disease. It is known to change cholesterol levels, cause blood pressure to rise, and lead to diabetes. So the first part of our exploratory data analysis is looking at the data structure. Overall, we have 70,000 observations. We have 12 predictors in 3 categories: objective, examination, and subjective. Our target variable is cardio, whether or not there's the presence of absence of cardiovascular disease. Within our data cleaning, we found there are no missing values, there are 24 duplicate records, and there are outliers and inconsistencies in these following 4 variables: systolic blood pressure, diastolic blood pressure, height, and weight. We conducted 2 univariate analyses and 2 bivariate analyses via data visualization. For univariate analyses, we looked at the histogram of all the numerical variables and for a count plot of all the categorical and binary variables. Then for bivariate analyses, we looked at pairs-wise scatter plots, which looks at the possible correlations between the 2 variables, and a correlation heat map that looks at all of the possible correlations. It is important to note here that we did not find any significant correlation between any 2 variables. Then within feature engineering, we were also able to create body mass index, which uses weight divided by the height, and blood pressure.
Before using any models, we split our data into training dataset, validation, and testing dataset. And we compared different supervised learning models, classification, and ensemble methods, support vector machines, and principal component analysis using grid search. And in addition, we also use principal component analysis to extract 95% of the variance in the data to help with the reducing the dimensionality. And to compare the results of the classification models, we computed the recall, specificity, precision, balanced accuracy, and F1 score for each of the models and used the highest average score between all metrics to determine the best model. And for each of these supervised learning and any other models, we created heat map and line plot to compare the results. And for supervised learning, we used naive-based linear discriminant analysis, logistic regression, k-nearest neighborhood with passing hyperparameter tuning and using research. And we also applied it with the PCA, principal component analysis. And we get the results for each of the models, average score, recall specificity, precision, balanced accuracy, and F1 score with the heat map and a line plot. And the best model out of this supervised learning, we get the logistic regression. We also compared support vector machine models, passing linear RBF sigmoid and polynomial kernels. Hyperparameter tuning was applied with the grid search and passed C values and gamma values. And we also applied principal component analysis. We get all results for support vector machines with the heat map and the line plot. And these plots show that the best support vector machine with the RBF kernel. We also compared bagging and boosting classifiers. For the bagging classifier, we specifically passed a grid search and randomized search for random forest, and bagging classifier with the decision trees as a base estimator. And out of this bagging classifiers, we get the randomized search for random forest as a best parameters and achieve better results. But the runtime drastically lower than grid search, but preferred slightly better than the grid search. And we also compared boosting classifiers using AdaBoost and gradient boosting and hyperparameter tuning parameters past learning rate and number of estimators. And we created the heat map and line plot for this bagging ensemble methods. And the better model, the best model out of this ensemble methods, we get the gradient boosting classifiers. And out of 34 models, the gradient boosting classifier with the default parameters achieved the better results in predicting disease. And the heat map shows the scores and compare the scores for each of these models. And this is the line plot for each of the model. And the gradient boosting achieved the better results.
Next, next, we wanted to discover some interesting and meaningful subgroups. So we used a cluster analysis. We performed k-mean clustering, and we tried different number of clusters. Among them, 3 number of clusters performed better. Looking at this graph, you can see that we use a silhouette value, and the average silhouette value is around 0.36. And we also compare the size of clusters, and you can see that the size of clusters are kind of similar. And then we try to interpret the segments using the centroids of clusters. And you can see that, for example, for cluster 0, it has mostly patients with higher blood pressure and other medical metrics, while cluster 1 has contain younger patients with a lower blood pressure, cholesterol, and some other metrics.
Then to help identify some key variables within our data set, we decided to take a principal factor analysis approach. So the first part before conducting principal factor analysis was looking at the distribution through a histogram of the 2 different groups, whether the presence of cardiovascular disease and the absence of cardiovascular disease. Because of all the overlap that we see using the histograms, we concluded that it's difficult to see any differences between the 2 groups. And the same thing we found looking at bar plots of the categorical variables and the binary variables. Then to conduct principal factor analysis, we use the first 2 principal components of each of the data set to identify common variances within the data set. For cardio equals 0, we found that the first principal component had positive high values for height and weight, and the second principal component had positive high values in age and systolic blood pressure. But for when cardio equals 1, for principal component 1, we found a dichotomous scale at a positive value for age and a negative values for height and weight. Then for principal component 2, we found positive values for both systolic and diastolic blood pressure, which signifies that there are significant differences within the common variances and further analysis is required. However, because we were only looking at 5 numerical variables, it is difficult to group into a single variable for further interpretation. All in all, for predicting the presence or absence of cardiovascular disease, the best model we found was gradient boosting classifier. For clustering analysis, we found that there are 3 clusters with noticeable differences. And for principal factor analysis, there are differences between the common variances between the 2 groups when cardio equals 0 and cardio equals 1. However, there are several things to note. One is that there are questionable data within our data set. The minimum for height we found was 55. The minimum for weight was 10. And we found there are negative values of blood pressure within our data. Thank you for listening. Please let us know if you have any questions or comments. And here are our reference list.